Okay, well, let's get started. Welcome, everybody. A reminder, we have no class next week. The 13th, I'm going to be headed for Eastern Washington. So, and when we come back, we will be starting to put all this stuff together. Should be fun. Now, let's review power, decibels, and capacitance. Now, how many people remember this? Does anybody remember this?
Everybody speak out.
Nobody's going to, and nobody remembers it, huh? Well, there's 4 things you have to remember. You need micro, which is the funny-tailed U there, which is 1/1,000,000th. We remember milli, which is 1,000th, and it's represented by a small m. And then we have kilo or kilo ohm, K, which is 1,000. So if somebody say you have a 470K resistor, that's 470,000 ohms. And then we have mega, like mega ohms, 2.7 mega ohms. And that's represented by a large M, capital M. Know this, please. Now, I want to take another stab at S units because I've been trying to explain this. And honestly, folks, I got stuck in the details of trying to show you how this works. But S stands for signal. And S9 is on your, and these are the meters that are on your radios. And they're either going to be an analog meter or they're going to read out digitally. But on HF radios, S9, which is a strong signal, is usually 50 microvolts. And every radio I've worked on so far that I've had to do any adjustment has an adjustment for that. So you can actually set it so when you're putting 50 microvolts into it, it'll read S9. Now, if you have S9 plus 20, that means plus 20 dB, which means the signal is 100 times stronger than S9. So instead of 50 microvolts or 500 microvolts, which would be plus 10, it would be plus 5,000 microvolts for a S9 plus 20 dB. Now, here's the thing that I've been trying to say to you. If a transmitter is reading S9 on the receive end, and at the other end, you've got a 100-watt peak envelope power transmitter, and you reduce that to 5 watts, that's minus 13 dB. That's a power ratio, power in watts. The S meter would drop to just below S5. Now that, and Scott will confirm this, that's a good, respectable signal. If you are working in emergency communications and all you've got is a battery, switch to low power. It'll save you a lot, and it may not cost you your communication. Only go back up to high power if you need to punch through the noise or whatever's going on. Now, when you're using HF and you're on and you're operating, people want to know what your signal report is. So when you report a signal, you would say, for instance, you're a 5x9. This means that the signal is perfectly copyable. It sounds practically like you're in the room with it. and you got a strong signal, which is an S9. So the first number is how readable your signal is, and the second number is the signal strength. So if you were to say it's a 4x3, that means you're having just a little bit of difficulty understanding what he's saying, and it is a weak signal. It's only on your S meter, S3. So that's your signal strength read on your receiver. That is how it is normally done. If you're in a contest, it's common for everybody to give everybody the same signal, 5x9. It's just done to save time and speed things up. Or you can actually, if you want to, give a real signal report, but that's typically what's done. So any questions on S units from anybody? Good, silence. That either means everybody's totally stupefied or they understand what we're talking about. Now, power is measured in watts. We know power because if we got a heater and it's 1500 watts, that's 120 volts times 12.5 amps, and it puts out a lot of heat. That's a lot of power. And if we're talking about our radio, and this is the one that I want you to remember, power is equal to E squared over R. Now, what is E?
Volts.
Right. Now, on to dB. I keep saying this, hopefully you will understand, but dB is used in many, many ways in amateur radio. It has to do with your antenna gain, your power output, all kinds of stuff. So, but just remember these things. For every 3 dB in power ratio, in other words, if you go up 3 dB or, up double your power or cut your power in half, that is 3 dB. For every 10 dB, it is either 10 times the power that you had or 1/10 the power that you had in watts. If you can remember that, you can figure everything else. If you got 6 dB, that's 4 times the power. If you have 9 dB, that's 8 times the power. And you can see the progression. You go 2, 4, 8, and then 10. So now, if you're going to measure voltage or audio, that would be 6 dB. But remember, the previous one is E squared. It's you take the voltage in, you square it. When you're talking about voltage, it's just a standard multiplication of voltage times resistance or whatever it is. Anyway, 6 dB is the same thing. If the voltage ratio is 2 to 1, either 2 times what it was or half of what it was, it changes 6 dB. Now, the way that works out, though, is that when you get to 10 times, it's 20 dB. And so the same thing, if it's 10 times whatever the unit power is, whether it's voltage or audio level or whatever, it's 20 dB, or if it's 1/10, it's minus, excuse me, this is something I should have told you. If it's less, it's minus 10 dB. Same thing on the 3 dB, it's plus and minus. So on S9 on your HF radio, it should be set at 50 microvolts. And it was, by the way, I believe that was Collins Radio many, many years ago that first used that. And they became the standard of the industry. But some of us old timers remember the old Collins S-line radios, the old tube radios. And anyway, a strong signal was 50 microvolts. Anyway, if you drop to S8, that usually drops to 25 microvolts. And it's that simple. Any questions? Silence? Good. Okay.
What does your meter on, say, your radio read? Is that's reading in microvolts?
That's correct. Actually, what the radio is looking at is your automatic gain control voltage. Let me explain what AGC is. I wasn't prepared for this, but let me give it just a thought. Automatic gain control, what it does is keep your audio level fairly at the same level. I hate using the same word twice, but so if you have a fluctuating signal coming in, which is pretty common when you're going through the atmosphere, your AGC keeps your sound level at about the same. So if you've got a strong signal, we'll say an S9 signal, that's good. But if it goes up, let's say it goes up 20 dB plus 20, that's an extremely strong signal. Your audio, if it wasn't for AGC, would go up that much. And you really don't want that to happen. So the radio sees that strong signal, applies a voltage to your IF, your intermediate frequency. And for those who are new to this, the intermediate frequency is something that radios use to amplify a signal. You start with an RF, you mix it to an intermediate frequency that's always the same frequency. And so that voltage that's used to control the IF is the same one that runs your S meter. So if you get a stronger signal, it lowers the gain of your IF. If you get a weaker signal, it raises the gain of the IF. And that's the signal that the radio is using to give you your S meter. Did that answer your question?
Yeah, I did, and it explains on my 7300 if I'm talking or on the net, somebody's got a good strong signal, and then a weaker station comes in, the radio actually increases the volume, or it sounds like it increases the volume.
That's exactly what happens, and that's what's happening. Your radio has slow AGC and fast AGC, and you can actually, in many radios, you can actually turn the AGC completely off. But slow AGC is what you want to use for voice. And fast AGC is what you want to use for digital and CW. Any questions? All right. Now, this is my signal generator. And there is this dial on it. And we're going to be using it here in a little bit. In fact, get ready, John. I'm going to have John actually test a couple radios, and we're going to not only check the power output of the radio, but we're also going to check its ability to receive signals.
Well, to quote Daron, you just tell me what to do.
Okay, so let's take a look at that. I'm going to change cameras. Should be the one. Yes. Okay, John, come on up. Now, what we're looking at, we've got three radios here. We've got this is my transceiver that I have from home, and I was checking it out today. This is the one that we've been watching the S meter on. Here is my mobile HF rig. And we will be checking this one, and maybe this one. We'll see how John does. We have two oscilloscopes here. This is a Tektronix. They're both Tektronix oscilloscopes, but this is from, my gosh, the 1970s and 1980s. This is a 7000 series oscilloscope with lots of plugins. These are two time bases here, and this is a vertical, and this is a vertical amp. And we'll be using this vertical amp and this time base here. And of course, it reads out over here. Now,
Joe, I hate to interrupt you, but you're
Yes.
pointing to the screen, I think, so those of us on Zoom can't see you pointing towards the instrument.
actually, are you not looking at my picture?
No, we're looking at all the test equipment there, so you'd have to turn around and point to the actual instrument for us to see it.
Okay, what's happening? You all need to pin me.
No, that's still okay, but you still have to point towards the instrument because the camera from you is showing both instruments and all three radios.
Yes, I know, but I'm using my mouse to show what's going on the screen.
Yeah, we can't see that though.
Oh, you can't.
No, we can't.
Oh, sorry, folks. I don't know what to do about that, but I'll tell you
Well, I
what.
can point.
Just turn around,
Here, let me.
turn around and use your right hand to point at the
I'm going to
screen.
do that.
All right.
Over here. Yes.
Sorry, Joe.
Oh, here, I thought I was showing you with my mouse on my computer. And that's the only place it shows up. Oh, for crying out loud. Okay, now, am I in the picture?
Yes.
Well,
your
my
hand is, yes.
My hand's in the picture here. All right, this is an oscilloscope. This is the 7000 series oscilloscope. These two amplifiers here are vertical amplifiers, and these are horizontal amplifiers. The horizontal gives you your sweep that goes across this way. In fact, here I'll see how that's going. You can actually see that moving. In fact, watch me. I want to change cameras. Now, can you see that
Yes,
here?
very good.
So this is the horizontal, and you can actually see it moving, so that you know it's time. It's done by time. See, it says 50 milliseconds per division. So there's every one of these divisions. Actually, John, you want to turn that down a little bit? More. There. Can you see the divisions now?
Yes,
Yeah, so it's 50 milliseconds per division. And so I'm going to increase that until we get up to 2 milliseconds per division. And that'll be a real good display for audio, because because of the frequency of our voice. And then the vertical display is, this says 5 volts, but actually it's 50 volts per division. I've got an old probe on it that doesn't have the little pin that tells it it's a 10 times probe. So the oscilloscope is 5 volts per division, but the probe turns it into 50 volts per division. So this is 0, plus 50, plus 100, plus 150 volts. And then this is 0 again, minus 50, minus 100, minus 150 volts. So this is amplitude, and we're going to be looking for the peak. So, and then there we go from this peak to this peak, which is peak to peak. So, has everybody got that down? Hopefully. All right, now I'm going to switch back to the other camera. Now, I've told you about the oscilloscope. Now we have three transceivers here. This is the one where we've been showing the S units, which is should be able to see, yes, right here. And so this is the meter that we've been watching. This rig right here is my home HF rig. And I use that for my RF seismograph. This one is the radio I use in my Suburban. It's my mobile HF rig. So we're going to try testing each one of these. Now, let me get out of here. And I'm going to have John start hooking these things up. So step in here, John. Don't trip on all the wires.
Joe, do you have those things insured before he does this?
No, if he blows it up, I'm going to take it out of his hide.
All right, be very careful, John.
I will be.
Okay, now, one thing I want you to do, I want you to look at the back of this radio,
All right.
my radio, because I want to have you do my radio first.
Oh, this radio, okay.
Notice there's nothing hooked up to it.
I see no amplifier, no antenna hooked up to it.
Yeah, so we need an antenna.
This one?
No,
No, that's not it.
no, that's not it. Here, John, over here.
Uh-huh.
See the dummy load?
I see the.
There's a wire that goes to the other radio over here.
Okay.
It's behind that, so you'll have to disconnect it. Now I'm gonna put him through this exercise so that you guys get an idea of what we need to do. So now he's going to put that on antenna 1, which is the one closest to us.
Okay. Antenna 1 is hooked up.
Okay, now you need to hook up the microphone.
Right.
Now I had the microphone disconnected for a very good reason. And I tested this out earlier just to make sure everything was going to work properly. Does anybody know why I had the microphone disconnected?
Don't want to transmit with no antenna.
That's one reason, but it's not the one I'm looking for. In fact, that's a good reason.
Microphone connected.
Okay, now can everybody see this screen? Okay,
The oscilloscope.
yeah. Okay, go ahead and switch it on and talk into it.
Test 1, 2. Test 1, 2, 3, 4. You can see the modulation on the screen, on the scope.
All we can see is something that's about 1/4 of an inch by 1/4 of an inch.
Right, now, do you want to see it close?
Switch cameras. There you go.
Now I can switch cameras.
Test
Okay.
1, 2, 3, 4. Is that better, Scott? Test 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Joe is the best teacher in the world.
Now hang on.
There you go.
Now you'll be able to see it better.
Test 1, 2. Test.
Yeah, you're talking too close to the microphone. Now,
Everybody's a critic.
yeah. Watch the scale over there.
Test 1, 2. Looks like about 100 volts peak to peak.
Yeah,
No, 200 peak to peak.
correct. Now talk to it right up to your mouth.
Test 1, 2, 3, 4, 5.
Notice how the tops are all flattened out.
Test 1, 2.
You're overdriving the microphone.
Okay, so if you step away from the mic a bit, you don't have as many flat tops.
Yeah.
Okay,
Okay, so what are the voltages you're looking at, John?
it's 100 peak or 200 peak to peak.
Yeah, so what do we do with the 100-volt peak?
Oh, well, we need to multiply that by 0.707. Is that what
Correct.
you're saying? Yeah, okay.
Then what do you do?
And you square that and you divide it by R.
Correct. And what do you come up with?
49, is it? I think, is it?
No,
What do you mean? What do you come up with power?
yeah, how
Yeah.
much power?
Whatever that math turns out to be, I don't know.
That's 100 watts.
It's 100 watts, okay. Yeah, 98, that's right. When we did the math, it was like 99 or something like that.
Yeah, okay. Now, I'm gonna have you check the sensitivity of this radio.
Okay,
So turn the transmitter off. Now, folks, we've been talking into a dummy load, so we're not going out over the air. We got a 50 ohm, at least 100 watt dummy load here, so we have no danger of transmitting where we shouldn't be transmitting. And dummy loads, by the way, are very handy things to have, and they're not very expensive. For 100 watt or thereabouts, they're under $100 typically. So now what we're going to do is we're going to check the sensitivity of the radio.
okay.
So what's the first thing that you want to do?
I have no idea.
Okay, disconnect the microphone.
All right.
Now, why am I having him disconnect the microphone?
Because we don't want to transmit.
Into what?
Well, you were calling John a dummy load, but I don't think that was very nice, but into your signal generator.
Correct. Yeah, I should have changed this. We have a very, very sensitive instrument, and we're going to put a 50 microvolt signal into. But can you imagine if you turn that around and you put 100 watts back into it? That's how you destroy signal generators.
Joe,
So-
just out of curiosity, does that have any protection on the output of the signal generator?
No,
Okay,
no, I have nothing. So when it says it's a 50 microvolts, it's 50 microvolts.
okay.
John,
Yes.
take a look at the signal generator and find the cable coming from it. No, that's not that one. The
Huh?
other. Oh,
This-
okay.
This,
This one right here, which is that one right there.
okay, which connects to there, to, which one is the signal generator, Jay?
That's the signal generator.
Okay, so I was in the right box, I just, okay, all right.
Now, disconnect the dummy load and hook it up to the signal generator. Not there, over here on the radio. Yeah, there you go. Now, we're going to have them take the output of the signal generator and put it directly into antenna A or antenna 1 on the
Radio.
radio.
Okay.
Now, is there anything showing up on the meter? Here, I'm going to so that you guys can hear this. John,
Yes,
see the frequency?
yes, it's 14.2.
What's the signal generator say?
14.1978. Yeah, it's right there at it.
Okay, is my radio in upper or lower sideband?
It is an upper sideband.
Okay, so the frequency that the signal generator is on right now is lower than the passband, so you're getting no signal. So what you want to do, see those two knobs? There's a big round one, and then there's that little one on the right.
This one?
Not that one.
Yeah.
Yes. tune that's a fine tune on the frequency. Tune it up to 201. Now,
201.
there's no signal. Oh, switch it on. I'm sorry. See that switch right there? Switch it to the right. There.
There you go.
Now, can you all hear that?
Yes.
Now I want to make sure. All right, now look at the dial on here, and it should be on 0.1
It's,
millivolts.
I'm looking where the reference is. Yes, it's
0.1
0.1
millivolts.
Yes.
Now on the right-hand side, see this needle here?
On the left over here.
Yeah, it should read out 5 on this scale up here. So turn this dial until it hits 5.
And it is at 5.
Okay, now look at the S meter on the radio.
And it's at almost, it's about S8. Almost S9.
Okay. That would, I'm sorry, but
Okay.
oh, it is reading a little bit low. Increase this until this reads S9.
This?
No, that's
This,
frequency.
yes,
Yeah.
right. Okay. It's about S9 right there.
Yeah. So what does the meter read?
The meter reads almost 6.8.
So that's 68 microvolts. So that's within what it should be. That's fairly close. So by noting that, I know that the receiver is basically working. Now, if you look at that scale and you reduce it, look at the lower scale
Okay.
on there. It says dB, right?
It does.
Now, take a note of where it is and then lower the power by 3 notches, which would be 3 dB.
Well, it says, maybe I'm not looking at the right place. It says dBm 50 ohms, the very, very lowest.
Yeah, no, that's what the scale is about. Read the scale itself.
Okay. The scale is just less than 0.
Okay, now reduce it by 3 notches.
Okay, and that's here?
Yeah,
So guys, if you can, there's a scope cable right in the view of the meter for us.
Okay. Here? No. Where are you talking about, Daron?
There you go. Thank you.
And now you said 3 notches. I have there's no detente on this knob for,
no.
okay.
Where it was here, come down 1, 2, 3 little notches.
And that would be 1, 2, 3. About there.
Okay, now turn around and look at the dB meter, or the S meter.
S meter shows S8.
S8.
So 3
So you
dB.
drop 3 dB in power, that's 6 dBV, or you drop the power in half. So drop it in half again, which would be 3 more dB.
Okay. 1, 2, 3.
Now what's it read?
It says 7.
So this radio is set up and is working properly for the S meter. Not all do that, especially the older ones, but some of the newer ones. And this is a particularly fine transceiver. So anyway, okay, now let's check my mobile rig. So turn off my radio. Press and hold the button for about. There you go. Now I'm going to have him check the radio, which is on the left side of the screen, the one on top of the power supply.
We only have one input, correct?
Correct.
It's gonna be a little tricky there, Joe. Move the power supply over just a wee bit.
You got it hooked up.
The antenna is hooked up.
Now you're going to have to change the power.
Okay.
Here's the power, and this is the one coming from the power supply.
Okay.
Now, notice, look at. I don't know how to do this, so you people out there can see. But in his left hand is the power coming from the power supply. And notice, show them the connector on the end.
It's a power pole.
It's a power pole connector. All of our radios should have those on them if you are involved in ACS. The reason is if you go anywhere, you should be able to just plug it in. So the power, and here I'll help you out, John.
Oh, here it is.
Yeah, he found it. Yeah, see how quick this goes together? You just plug them in. You just plug it.
You just plug them in, and I'm doing it. I mean, I've used these before.
These.
There we go. So we now have power.
Oh, there
on
we've got that radio powered up.
Hey.
Now, one thing you want to make sure is there a microphone hooked up to that
There's
radio?
a microphone hooked up to this radio.
Do not punch the button. Disconnect that microphone.
Yes.
We should have done that first. Because all he would have had to do is have that or have the oh, wait a second, what do they call that? I'll think of it here. What do they call it?
Are you thinking of the Vox?
Vox.
Vox.
Yeah, if the Vox had been on and somebody spoke, it would have transmitted into the signal generator. Okay, now set that radio to 14200.
$14,200.
Okay, reset it for 50 microvolts.
No.
That's frequency.
Okay, this one?
Yeah.
Okay.
So it should be on 0.1 millivolts. And it should be on the scale, since it's 10. And I'm afraid we don't have enough cameras to show everything.
It's
At
on,
5.
yes,
So that's 50 microvolts.
right.
Now tune the fine tuner on the. Now look at the radio. Is the power,
Is it what?
yeah, it's on. You should be able to receive it.
All right, so what do we want to do?
Well, you should be able to get the signal there. Oh, here, hey, let me do it, John.
Have your audio gain up?
No, but it doesn't. Oh, wait a minute. Yeah, there we go. See the signal there?
Mm-hmm.
That's what we were. Yeah. We should have had the audio gain up for. That's about plus 10 dB.
Yes.
Huh.
It should be right at S9, right?
Should be. Oh,
Okay, that's 10 over. It's still 10 over.
okay. We've got plus 10 dB. So now what we're going to do is we're going to grab. Here, I'm gonna turn this down to 9. Now what we're just going to do is we're just going to take this and turn this down.
Okay.
Now, can everybody still hear that?
Unfortunately, yeah.
Yep.
Oh, good. All right, we're down to 0.5 microvolts. I can still hear it. I don't know if anyone else. Now it's probably 0.3. So it's 0.1 microvolts, and I can still hear it. Now, if that were a CW signal, that would be perfectly copyable,
But not for voice.
but not for voice. It's not going to work. But you can see that the radio is quite sensitive. So go ahead and turn it back up to S9.
That's
Turn the big knob.
yeah, that's what there we go. Okay. That's S no. Okay. That's S9 right there.
Okay, good. Turn the signal generator off. Woo! Okay, set that radio up to test its power. I'm going to let him do it on his own now.
Oh, jeez. Okay. I'm sorry. I
Okay,
have to
then.
admit in front of God and everybody that I don't have a clue.
Dummy load.
Anybody want to help him? What should he do? Somebody?
Phone a friend, maybe?
A dummy load.
Scott, you said dummy load. What about the dummy load?
You want to hook a dummy load to the transceiver?
Yeah, John, do you remember that?
Whoops! I just disconnected the dummy load. Okay. So the dummy load's got to go to the transceiver.
John, I think you need a raise.
I'm telling you.
Hey, John,
What?
remember the antenna over here?
I do.
The wire? See the wire laying there?
Oh, there it is, okay. All right.
I'm sorry, I'm helping him out a little
Well,
bit.
that's good, because.
What's he need to do with the,
And then turn the radio off and connect this to it.
actually, you don't need to turn the radio off.
Oh, okay. So I'm disconnecting the frequency synthesizer from the radio. And I'm going to connect the dummy load, like Scott said. Now the dummy load is connected, so we can now
Now, what's he need to do next?
connect the microphone.
Yes.
By Jove. Okay. All right. So I'm ready to transmit into the dummy load.
Yeah, well, check and see if you're on upper sideband.
I am.
Okay, try transmitting. That's the wrong microphone.
Well, it went in the hole.
You
All right.
need that's a Yaesu
That's
microphone,
just for that. Okay.
and this is an Icon microphone.
So it is. Picky. They shouldn't fit in there if they're not supposed to be the ones for that radio. All right.
You don't have to screw that on there. All right, now go ahead. Don't stand so that you're in front of the oscilloscope. Okay, go ahead and transmit.
Test 1, 2. Test 1, 2.
Yeah, turn up the intensity of the. Here, let's turn this.
Turn the volume or the brightness up here. Okay, test 1, 2, 3, 4, 5. It looks like it's peak to peak is 200. I would say even over 200 at some points on the
Yeah.
test 1, 2. So it test
Say
1, 2,
say
3.
4.
4. Yeah, that's pretty much right at 200 peak to peak.
Yeah. So we've confirmed this radio will put out its maximum amount of power as specified. So we've determined that this radio and well, we didn't check the low end of my transceiver. I did earlier today, but
Okay, so for those of us who don't have oscilloscopes and frequency synthesizers and all those kinds of things, we just have to find somebody who does to be able to test our rig out, correct?
where would you find that kind of equipment?
In the barn.
Precisely.
So we want to encourage people to use the equipment that's here to test their rigs.
Correct.
All right.
We have, in fact, thank you, John.
You're welcome.
I'm going to show something.
Joe, I have a question.
Fire away.
How does the oscilloscope hook up to the radio?
Through a probe. And I'll, in fact, see right here? This is one probe and this is another probe. So this probe here is, here, I need to turn the volume down here. See this cable right here? This is a probe. Is it showing, John?
Yes, it is.
Okay.
Yeah, the screen is behind me, so it makes it hard to do. So, is this showing up in there, John?
Yes.
Yeah, okay, so,
Lower down, go down a little bit, unless you unless you're done. Yeah, that right there.
Yeah, okay. This is a dummy load. And this will take 100 watts all day, all night, full CW, and you cannot hurt it. And so this is considered a 100-watt load. This T I have in here, these are general radio connectors. I use these because I had it, this was an end connector. So I adapted this end to a BNC connector, which you can see right here. That's a BNC connector.
Right.
This is an adapter so that you can connect your probe to the BNC, and I just put this clamp here to be able to hook up the ground.
So with that adapter, whatever's going to the dummy load then also goes to the oscilloscope.
Somebody please mute. Thank you. This side is the coax that goes from here. It comes over to this radio, and so it goes through there. Now, somebody said, I'm sorry here. Somebody said, how do you do this if you don't have an oscilloscope? This is an SWR bridge. And hello, test.
Raise it just a bit. Your camera.
Pardon?
Raise your camera just a bit. There you go.
Okay. Now notice the it's reading on the meter. Correct, right there. This meter reads average power. You can get meters that read peak power. However, this one does not. I'm going to. Oh, by the way, that's a Variac. That's how we adjusted the light. You can get meters that read peak. Now they vary in quality and how accurate they are, but some of them are actually quite good. So if you get a peak reading one, there's electronics in it, and it reads the peak, and it'll show up on the meter as peak. So if you buy an SWR peak reading meter, you can put that in your system and you'll know how much power that you're putting out. I prefer using an oscilloscope. This entire oscilloscope that you guys have been looking at tonight, I spent less money on that than people will spend for a peak reading S meter. So I mean, they can cost $300, and I got less money and far less money. I've only got about $200 in what you looked at today. This oscilloscope is probably 40 years old or more. It was built probably, I'll just say in round figures, 1980. But Tektronix equipment is extremely good equipment, and it lasts basically forever with very little maintenance or anything. So you can get equipment, and you can get portable oscilloscopes like the one that was sitting next to it. In fact, there's the portable one, the little one sitting there. That's a I think it's 50 megahertz. Yeah, it's a 50 megahertz oscilloscope.
And Joe, there's 3 comments on the chat line. One, Prudence says that it's really hard on the ears when we had the tone, and Daron says that 1,000 hertz tone is used for testing like this, and yes, it means work is in progress to us technicians, but my wife is quick to point out that it is very annoying. And Don KB7KUH agrees wholeheartedly. Yes, it is.
Yeah, sorry, folks. You needed to hear the tone so you know that it's working. I usually turn the volume down on the radio so you can just barely hear it, or I turn it off often, but I leave it slightly on so I can tell it's working. And yes, it is annoying. But anyway, I think it's time that we take a break.
Joe, let me interject one thing if I can real quick.
Please.
So in the test equipment for me is an integrated service monitor designed to do this kind of testing. And the antenna input is a BNC connector. I had it in there. And I wasn't aware until I fired it up and used it. There is a little teeny, what looks like a resistor, but it's called a pico fuse. This is a 1/2 amp fuse in line with the signal generator portion. And that little teeny fuse kind of plugs into the back of that BNC connector, and that screws into the front of the instrument.
Oh, hey, Daron.
Yeah.
Yeah, hang on a second, because I've got me pinned, and everybody else is seeing it, but it's not going onto the video. So
Okay, hang on.
Pin
Here.
Daron.
so I need
So
to move. There we go.
that's the BNC for my signal generator portion of my communications analyzer, and it has a 1/2 amp pico fuse, which looks kind of like a resistor, but it's there just for the specific purpose in case you transmit into the signal generator portion, it'll pop that fuse and not damage the instrument.
Fabulous.
So it's part of the, some people that worked on this instrument obviously worked with me in the field at some point, and they realized, hey, we need some kind of protection on that. I did not know it was there. And as you could tell with John swapping cables tonight, it's very easy to swap a cable, test, transmit, and find out, whoops, wrong radio, wrong antenna, wrong something.
Correct.
I was very surprised to find this and very happy to realize that I could just replace this little teeny fuse in the connector itself and my instrument was fine. So we made a little progression with that for some testing, and it's very handy.
Yes. Yeah, you need to be very careful, and that is a wonderful thing to know. Jim Thorson.
Hey, quit.
Oh, Jim, mute, please. Jim Thorson. I guess I need to pin myself again here. Jim Thorson, who is an engineer for Daron, what kind of an engineer is he? He's does broadcast.
Yeah, I guess I would say about Jim that he has literally forgotten more about RF than I've ever known.
Yeah.
That's the kind of guy he is.
He's a perfectionist. He's an engineer. He worked for CBS television in Southern California for many years. Kept their transmitters running up on top of the mountains. He did all that kind of stuff. But what did you call your service monitor? Is that correct?
Yes, service monitor.
Now he found a service monitor online and purchased it for a very low price that needs work. He's working on it, and he's going to give it to the club.
Oh, wonderful!
For doing these things, and I'll let him train you on how to use it. So
well, it's a tough deal because I bought mine used for $3,000 probably 10 years ago, and I've certainly got my money's worth doing commercial and amateur projects out of it. But it is not a cheap piece of equipment, and it's very old. So
yeah, but it's wonderful to have. I used one for a while, but it was an extremely old one, and it was problematic. Anyway, let's take a break. 10 minutes from now, we'll get started on the second half of the class tonight. Thank you, everybody. Back to capacitors. Those wonderful little devices. Now, I hope you guys remember this, but I had a list of things you could do with capacitors. A storage device, a filter, a DC blocker, an AC passer, a timer, and I added a new one, a tuned circuit, but that didn't fit in with the A something. And anyway, I have added each one of these so that I can at least verbally explain what they mean. A storage device. Most power supplies use them to remove hum, because when you change AC into DC, you use diodes and you end up with this very lumpy DC. And by putting in a capacitor, it smooths it out, and so you get rid of the hum. And a question? No? Okay, a filter. They can be used for low pass filters. Now, this is in conjunction with inductors, which we will be talking to you or get started on tonight. So anyway, band pass filters, etc., that kind of thing. A DC blocker. DC cannot pass through a capacitor. Well, at least a capacitor that is working properly. If DC is passing through, you've damaged the capacitor. So an AC passer. AC goes through a capacitor fairly easy, but if it's a small capacitor and a low frequency, very little AC will go through. If it's a high frequency, lots of AC goes through. And we will be studying that next time we get together. I hope, Lord willing, here. It can be used as a timer. Now, you remember our experiments that we did with Daron last week. We hooked up a resistor and a capacitor, and then we charged up the capacitor, and it took X amount of time for it to charge up, and we watched that charge up. That's called a time constant. So if you multiply the resistor value in millions of ohms times the capacitance in microfarads. So if you have like 100 microfarad capacitor and a 0.5 mega ohm resistor, you multiply those together, you'll end up with 5 seconds. Anyway, that's how that works. And then for tuned circuits, now this is where it becomes critical that you use the right kind of capacitors, because you don't want them to be sensitive to heat changes and other things like this. But they're used in oscillators, RF amplifiers, and transmatches. Now, I said transmatch. Most people, unfortunately, call them antenna tuners. Well, they don't tune the antenna. They match the RF, the impedance of the antenna to the impedance of the transmitter. So anyway, any questions on this part? All right. Next, DC, AC, and frequency. Now, this is a review of what we studied before. Now, I see that my mouse is not. Oh, it is working.
Yes.
Okay. This is a sine wave. Here, I'm going backwards. We start at time 0. Instead of time, this is in degrees. So if you pretend like a circle, which has 360 degrees, you start out at 0 degrees, and you go for X amount of time, and at 90 degrees, you've got the positive peak. At 180 degrees, it's just crossing 0 volts, headed down to 270 degrees at minus voltage, and then back up again to 0 degrees at 360 degrees. So one cycle, this is going from here to here, is one cycle. And then we have, remember we were talking about peak earlier? We were measuring peak voltages, and then we have peak to peak. So we go from all the way from the highest positive to the lowest negative, and that's peak to peak. So if you know what the peak to peak is, you just divide by 2, and then you get the peak. And then the volts RMS. Basically, what you're doing is you're taking the power that's under here and turning it into DC. And this is a DC voltage, and it's 0.707 what the voltage peak is. And we're here, this next slide, I'll show you again what that means. Now here is a sine wave like this. And we just continue on through, and there's 3 full cycles here. Now, if you look underneath this section of the sine wave, we see some purple area and some purple or blue, whichever. And then we've got the volts RMS, which is in green. If you take the area of this and add it to the area of this, it equals the area of this. So if you take an AC signal and you measure the volts RMS, that would be the DC value with the same power level. So if you turn the AC into DC, it gives you the same amount of power. So, and that's 0.707. In this case, we've got 170 volts peak and 115 volts RMS. Now, frequency and wavelength. Here is a high frequency with a short wavelength. Here's a low frequency with a much longer wavelength. And I want to illustrate that to you again. This is the audio signal generator. And now I want to turn on the amplifier. Now this is again my signal generator, except this is on the audio side. Okay, now let's lower the frequency. Notice the wavelength gets short, and then we increase it. The frequency gets higher, and the wavelength or the time gets much shorter. I want everybody to hear that and see it and understand. Low frequency, long wavelength, high frequency, short wavelength. And I'm going to spare your ears. That's one demo we do not want to lose track of. I need a little bit of feedback. Are you understanding what I'm trying to show you? You've heard it and you've seen it. I see a couple heads shaking yes.
Yes, very good.
Yes.
Thank you. I appreciate that. Now let's go back to the Now back to this, back to capacitors. Remember what before I told you there's all kinds of capacitors, and there are capacitors with different kind of dielectrics. You can have air variable capacitors with air as the dielectric. You can have a vacuum as the dielectric. You can have all kinds of materials. Like, do you see this ceramic capacitor here? The dielectric is a ceramic. There's a polyester that uses polyester for the dielectric, polypropylene, and here's polystyrene. Each one has a usable dielectric that has characteristics that are usable for different things. Now, this is something I did not show you before. These are dielectric constants. Vacuum has a dielectric constant of 1.0. It is the reference for dielectrics. If you put air in, it's pretty much the same, 1.0006. I've seen 1.007 also. So dry paper is 2 to 2.5. Glass is 5 to 10. Mica, which is a very common transmitting capacitance, it's very stable, 3.0 to 7.0. So, we go through the list with the difference from Teflon. I've taken Teflon and actually built a capacitor that had a very high voltage handling capability, and for making Dave Sanford's antenna work. We could not find a capacitor to do it, so we just figured out the area. We had the thickness of the Teflon material, and we stuck it between two plates and made a capacitor. So I do not believe that this is on any of the tests anywhere. But you will remember this, because now Daron did this last time. We charged up a capacitor right here. This was a for Daron's test, it was 100 microfarad. And then we had this resistor here to both charge it and to discharge it. And I think you used about 470K, Daron?
I don't remember, Joe. Sorry.
Oh, that's all right. I think that was about what it was. I think we had figured 50K. So that would have been 0.5 megohms times 100 microfarad, which would have been 5 seconds. But anyway, now this is something that you who are planning to get your extra need to know. The figure for one time constant is 62.8% of the voltage value that was either charging the capacitor or on the capacitor and then discharged. So when the voltage drops, or raises from 0 to 62.8%, that's one time constant. And that's a given, and that's on the test. So you folks that are planning on getting your extra, remember that. And here are two tables. It's 60, I made a mistake, it's 63.2%. So if you charge a capacitor through a resistor, you start out at 0 voltage, and this is time and time constants. At one time constant, it will be 63.2 ohms, my mistake. Two time constants will be 86.5. But now notice the distance from here to here and from here to here, this is much shorter. And then when you go to 3 time constants here, the time is, the voltage change is much less. By the time you get to 4 time constants, it's 98.2%, which is almost fully charged. A capacitor is considered to be fully charged after 5 time constants, which brings it up to almost 100% of the voltage that it will charge to. And also, if you're going to discharge through the same resistor, it's the same thing, except that for the first time constant, which is here, that's 36.8 volts. And as you can see, it discharges exponentially until it's fully discharged at 5-time constants. So we're going to be looking at inductors here shortly, and they have a similar curve, except that it's for current through them, not for voltage.
Joe,
So
can you switch your audio back to non-musician, whatever it was?
Yes.
Because we're getting a lot of background noise that we probably don't need if you're not showing the tone or sharing the tone kind of things anymore.
Yes. Hey, anybody notice anything like that? Just let me know right away so we don't have to endure it. So now let's see back.
Excellent. Thank you.
Joe, can I have just a question on the dielectric constant?
Yes.
So the lower the constant, does that, if it has a lower constant, is that a more effective dielectric, or is it the other way around?
Actually, it's the other way around.
The higher the constant.
Yeah,
Okay.
The one thing that I didn't want to do is to get into the formulas for figuring that out. But there are formulas. You can take the area of the capacitor either in inches or in square centimeters. And if it's a vacuum, that's probably the lowest. But when
Okay.
you put a dielectric in, it increases with the increase of the number of the constant of the dielectric. So if you got a dielectric with a constant of 2, you would get double the capacitance for the same spacing.
Okay, got it. Thank you.
All right. Are we ready to go on to inductance?
Yes.
Oh, good. Oh, good. I'm glad somebody's ready, because I was ready to go home. I'm ready. Hey, guys, I'm getting tired. Anyway, when you run electricity through a wire, it generates a field around it, and it is a magnetic field. So now remember, with capacitance, they had a electrostatic field. When you charge them up, they'd have a field around the capacitor that was, and if it was fully charged, it would have been the voltage of whatever is charging it. So now I'm hoping that all of you have read this in the book. This illustration is showing a wire, and this particular one here is showing conventional current flow going from positive to negative. In that case, you would use the right-hand rule. If you grab that wire with your right hand and pointed your thumb at the negative, the direction, your fingers would be in the direction of the flux line. So the problem is, and this is a question that's on the test. And remember, I talked to all of you about electron flow, or electronics current, which was the electrons flowing one direction in a wire. And then I talked to you about hole flow, which was conventional current flow, which was from positive to negative, going the opposite direction as the electrons. One is the electrons moving through the wire. The other is the holes that are generated by the electrons moving, going the opposite direction. This is something important And honestly, folks, I didn't get this for many years, and it left me really confused. But once I learned what was going on, I was able to figure out, okay, what's this person talking about? The problem is they're in the book, they are showing this using the right-hand rule. But E5D06, and they say this in the text, is using electron flow left hand. So you point your thumb toward the positive, but notice your fingers are still pointed the same direction. John, right hand,
That's the way I always learned it.
left hand, or left thumb, right thumb. Notice the fingers are pointing the same direction. You get that, John?
Sure, if you reverse your hands, yeah, okay.
Yeah, precisely. The thumb, my left hand is showing electron flow. My right hand is showing hole flow, conventional electronics, and conventional current flow, electronics current flow. This is the flow of the electrons. This is the flow of the
Holes.
holes. Is that how many people are confused? No one? Nobody would.
You know, I always thought I learned it
Well, I think you did.
with the diagram you've got there, but you have with the positive on the left end and the negative on the right end.
Oh, are you able to see this? This is the. Are you telling what it should be? Or are you telling me?
Oh,
what
I'm
should
just saying
be?
what
This is
I
negative on
learned.
this side, and this is positive on the right side.
Okay.
And they're showing conventional current flow
Right.
from positive to negative. But when they talk about it in the text, and they're talking about this signal right here, not this, I'm sorry, I'm getting tired. When they're talking about this question, they're using the right-hand rule, which is from the current is flowing, the electrons flowing from the negative here, this direction to the positive. And you end up with the flux lines going in the same direction. I hope everybody understands that.
To me, it looks just, it doesn't look like that. If I'm starting in positive, and like this diagram shows, then, and if I'm standing at the positive end, the arrows are going clockwise. If I'm standing at the negative end and I reverse the flow towards the positive end, the arrows are going counterclockwise. They're not going in the same direction.
That's because you're looking at the opposite side.
Yes.
You're looking at the opposite end. That confuses me also.
Okay.
That's why they say use the hand. If you use the hand, it'll point in the right direction. And that can become important. But let's move on. What is inductance? I found this and I like this because it shows three different things here. First of all, here are the schematic symbols. Here is an air core inductor. Here's one with an iron core. This one's with a ferrite core. And this is a variable core. And shortly here, I will show you some of these in the real world, what they are. But if you take a wire, this guy here, and you wrap it in a circle like this, every time you go in a circle, the current, the magnetic field that's generated in this wire then joins this wire, which in turn joins this wire, and so on and so forth. And so every time you put a coil on, you build the strength of the magnetic field with the same current. So the current just goes through here, and it generates a stronger magnetic field. Now here is a coil. And this is the magnetic field around the coil. And this is N. N is the number of turns. I is the current through it. And E is the voltage across it. And here they're showing a DC volt being applied. So you apply the voltage, the magnetic field gets set up, it spreads out, and then it stops spreading. But it stays fixed. So let's, and remember, folks, at this point right here, we're just getting into how these coils work. Now, this is the reason it's important for you to learn. What I'm showing you here is a radio signal going through the air. Starts and an antenna is over here, and over here, excuse me, over here will be a receiving antenna. And this is the signal going through space, whether it's air or through a vacuum, it doesn't matter. Now, see this blue line here?
Yeah.
That's the magnetic field generated by your antenna. The electric field is perpendicular to it. They're 90 degrees apart. And so here it comes down, up, and this is the electric field. And this would be a vertically polarized antenna. At least that's how I see it. If you twist your antenna 90 degrees, it would then become a horizontal. If the elements are horizontal, then the electric field will be horizontal. But we will, when we get into antennas, we will discuss this in great detail. But remember, these fields are important to a radio wave signal. And we need to start getting them into our brains so that we understand what's going on. Now, this is, well, you remember this from last week? Darren pointed out to me, Joe, you got the wrong display. We're not going to do tonight a display. I hope that I can, on an oscilloscope, show you how this works. We can't get a big enough inductor to make it go slow enough to make it work. But when the switch is open, when this switch is open, no current can flow through this. Either electron flow this direction or positive flow this way. But current going through this inductor will produce a magnetic field, and the resistor will limit the amount of current, because an inductor is usually nothing but a piece of wire, and it has a very low resistance. So if you don't have a resistor in here, you can draw a lot of current in a big hurry. So the R with the inductor creates an RL time constant, just like for capacitance. Okay, here are a few inductors. All kinds of them. What do you think, huh? Let's get started. Here, let's start with this one here. This is actually, this was taken out of a piece of equipment. You can see solder here, here, and here. This was actually the plate circuit of a push-pull, I think VHF radio transmitter. But this, you can see the coil here coming up. And at this point, it reverses and goes the other direction. So that was in a push-pull application, but this is a coil. And it's an inductor. So, but this is a very low Henry's inductor. We might even test these after a while. So let's just talk about the ones from transmitters for now. Here's one. This you will find in a high power transmitter. This is wound so that this does not become resonant at any specific frequency that this transmitter was. But they use this to keep RF off of the DC. So here's a high, I'm trying to say high frequency. This is not right. This is a high inductance. There's a lot of turns, little tiny wire here with many turns. This was an old one. Most of these are. This is what's called an RF choke. This is also an RF choke, but this is a very specific one. This one, and this is an old style, but it's got many fine turns and will keep RF from going from this side to this side. Now, this is what you will find in your new radios. This kind of thing. We've got a core with windings around it. So if there's lots of winding, it's for a lower frequency. If it's got a few windings, it's for a higher frequency. But this is, we'll get into more detail on this later. Now here's a couple of them. This one, I've got a whole slug of these. And there's, I forgot, I've measured this and now I've forgotten what they are, but this is a coil inside of a powdered iron core. So, or is that ferrite? I'm not sure. Here's an air core with many turns and just 2 wires. So that's a higher. Now, remember the ones that we showed the schematic and it was adjustable? See the black inside there? And that's a hexagon. It's 6-sided. That's a standard tool that you use for adjusting this. By screwing that in and out, it changes the inductance of this. This is basically the same thing, but it does not have a core. This is a much lower inductance than this one is. This one would have more just by the more windings on it, but because it has the core, its inductance is way higher. So now, remember the surface mount? Oh, here, let me show you this first. Here are some little tiny 220 microhenry inductors. Now here is a surface mount. This one's 33 nanohenry. And this is 10 microhenry. And these are surface mount. And these are the kind of things that you find And here's another one, little tiny ones. Let me see if I get them spread out a little bit. These little tiny guys, these are the kind of things you'll find in your handheld radios. And also, I'm sure that my transceiver has some of these in it also. The Yaesu. Now, I'm going to get all of these out of the way so that I can show you this. This is a variable inductor. Of course, we have the coil. We'll recognize that as a bunch of turns. But then we have this roller here. And this is a contact. And as we turn this, this moves up the coils. And this is the output right here through this wire. So it changes the inductance. Many of your transmatch or quote antenna tuners have a device like this inside, and that's how you change the inductance of your transmatch. Now, this is a very old one, but I know a lot of people like to get their hands on this to build a transmatch, which a lot of amateurs do. Now, I'm going to show you a output circuit for what is called a Heath kit. And these are fun. There's this large coil here, and then there are these smaller ones. Now this large core here is designed to work on 10 meters. And this part here allows you to work down all the way through 80 meters. And this is the output stage of a Heath SB220. It's a 1500 watt transmitter, and there are two 3-500 tubes in here. They're tubes that are about, excuse me, about that big around. And they're, well, they're much longer than I can get far enough away. But I want to show you something. There's a switch here that allows you to switch in whatever part of this coil you want to use for the frequency. Inside of here, this is on the input side of the transmitter. Now, notice that inside of each one, there's a ferrite core. On this side, you can stick a probe, adjuster in there, and you adjust this. So, yeah, I'm trying to see if I can figure out. You have one of those for each of the bands. It would have been 80, 40, 20, 15, and 10 meters. Those are the 5 bands that this old rig would have been designed to work with. So I see this coil here. This has the fewer turns, so I'm going to assume this is the coil that's used for 10 meters because it has the lowest inductance. And I'm going to assume that this one here, which has the most turns, and I see some capacitance across it also, for 80 meters. So this portion of the radio pre-tunes what goes into the radio. And then on this side, these are the parts that work with the power and the output for the transmitter. So that's an old SB 220, 1500 watt transmitter. Now this, and we're almost out of time. Does anybody have
Joe,
any questions?
do you mean amplifier?
Well, yes, what did I say?
Transmitter.
That is correct.
Okay, I was gonna
It's an
say that looks a
amplifier.
lot like the inside of my SB221.
Yeah, yes. Well, the 221 did not have 10 meters because unless you
Mine does.
modified it. Don, you were going to say something?
Oh, my SB221 Heathkit goes from 80, 40, 20, 15, and 10.
Correct. And my SB 221 does the same thing. But the 21, originally, if you bought it, it did not have 10 meters and you had to add it.
Okay.
And the reason is because CB radio operators were getting it and using it on 11 meters, which is a band and a service that's only permitted legally 5 watts.
Right.
So if you can imagine 1500 watts where only 5 watts is permitted. I saw an SB either 220 or 221 that had been modified to work on
11 meters.
yes, on 11 meters only, and it had five 3-500s.
Whoa.
Whoa is right.
Is 3-500 a tube?
3-500 is a tube. And the 500 means that the plate will dissipate 500 watts. So potentially that transmitter could have put out 5,000 watts.
Yeah, they sure have hacked up a lot of good linear amplifiers doing that.
Yep, yeah, they did.
Hey, Don, are those tubes, do you remember showing me your tubes? Were those 500s?
Yeah, those are the 500 tubes.
Pretty
Okay.
expensive.
The 3Z500.
Yeah.
I can unbox one real quick if y'all want to see one.
Well, can you do? Well, let's save it for next time because
Okay.
we've just got 1 minute left tonight, and we need to close down. So anyway, but let's plan on that for 2 weeks from tonight. How's that sound to everybody?
Sounds good.
All
I
right.
was shocked.
We're starting to see how these things start coming together to generate the stuffs that we use for amateur radio. And so next time we're going to be talking about reactance, and that's the reactance of capacitance. That's X sub C, or X sub L, the reactance of inductors. And as I talked about earlier, if you have a capacitor and it's a low frequency, it'll let some of the low frequency through. But as the frequency goes up, it lets more go through. So the reactance decreases as the frequency goes up. And the opposite is true for the inductor. So those we will be learning, and we will apply them. And we'll also be talking about impedance, which, like our radios are usually intended to work into 50 ohms impedance. And our antennas, if they're, well, now I should not say that. We should be able to take our antennas and make it match 50 ohms impedance, because that's what our transmitters are putting out. And by the way, if you have two of the same impedance that creates your maximum transfer of power. So that's our desire to do that. In resonance, that's when X sub C and X sub L are equal, that is resonance. But that is a very important part of knowing amateur radio and how it works. So that's it for tonight. Any more questions?
No,
Good
just
job.
thank you and have a safe trip next week.
Thank you. Yeah, that starting to get a little long on the tooth. That wears on you quite a bit, but it should be a nice trip. We have all day Friday to get to where we're going. So anyway, well, God
What
bless
part of
you all.
Washington?
Pardon?
What part of Washington are you going to?
Clarkston, Washington, which is right on the Idaho border.
Ah,
And Lewiston is the town that's on the other side of the river. And you can imagine where they got their names from.
Yep.
So Lord, thank you for for a good night tonight.
Thanks, Joe.
Amen.
Thank you, Joe. Everybody have a good evening.
Thanks, Joe. Thanks, John.
Oh, thanks everybody for coming.
Much appreciated.
Great assist there, John. Good job.
Oh, thanks.
Well, we're
What
all,
about my work?
hey, I want you
didn't
all
have
to
to
know
do
we're all
anything.
learning, including me.
Yeah, I'm just Van White.
Good night.
Have a good
Good night,
one.
everybody. I'm going to get on HF and play around.
Have fun.